We will discuss the satellites, how the different things about the satellites. Actually, suppose if this is the body of mass m around which a satellite of mass m moves. This is the mass m of the body which moves with linear velocity v, and this is the orbital radius. Orbital radius of the satellite. This is the orbital radius of the satellite. Now, when the satellite is moving the circular path, clearly this satellite is provided the centripetal force by this thing. So, centripetal force is here, and centripetal force is actually the force of gravitation between these two. So, this is the golden equation. I can write mv square upon r is equal to gmm upon r square. This is the centripetal force, and this is the gravitational force between the body of mass m and the satellite of mass m, and also I can have an mr omega square. So this is the golden equation, known as the golden equation of the satellite. Why we call it the golden equation? Because we can derive actually all the things from this, all the parameters, all the different things will be seeing. Majority of the formulas will be derived from using this equation. For example, the first thing is, suppose I have to find what is the linear speed of a satellite. If I want to find the linear speed of a satellite, I will definitely go to the golden equation. Golden equation tells us it's mv square upon r is equal to gmm upon r square. So m is cancelled with m. So v square is equal to gm upon r square into r. This r cancel out into square of this. So v square is equal to gm upon r. So v is equal to gm upon r under the root. This is the one formula. Other formula I can write this. Suppose I can have written this gm upon r. I can multiply and divide it by r. So this I can calculate v is equal to gm upon this will become gm upon r square into r under the root. So but this is actually g, so this is g r under the root. But keep in mind, when you use this formula, g is at the point where satellite is revolving. So g will be in that case that thing. G is not other thing on the surface of this planet. G is at this point where the satellite is moving. So I can always say this is the linear speed of the satellite. Just mv square upon r is equal to g upon r square, and v square g upon r square, and v square g upon r. So v is equal to g upon r. In order to find the form of a g, I just multiply it and divide by r. So g upon r square and r, so g r under the root. It's the linear speed. Now, how can I find the angular speed of a satellite? The same satellite, there's the angular speed of a satellite. How I can find the angular speed of a satellite? Now, for angular speed, I can write mr omega square is equal to gmm upon r square. M is cancelled with m. So mass of the satellite is usually cancelled. So many things are independent of the mass. So I will say omega square is equal to gm upon r cubed. So omega will be equal to gm upon r cubed under the root. This is nothing but the angular speed. So for angular speed, it's very simple. I can just write mr omega square is equal to gmm upon r square. So omega square is equal to gmm upon r cubed. So omega is this one. Now I can find, suppose, how the time period and orbital satellite are related. How the time period of the satellite. Now when we want to find the time period, we'll be proving a very basic law of the satellite, that is t square is directly proportional to r cube. Means square of the time period is directly proportional to cube of the orbital radius. This is the famous Kepler's law. Sometimes examiners do not use the word Kepler's law, but they say you have to prove square the time period is directly proportional to cube of the orbital radius. Now that's very important. Usually it comes in A-level exam. The key is again go to the golden equation. mr omega square is equal to gmm upon r square. So this m is cancelled. So omega square will be equal to gm upon r cube. Now omega is equal to 2 pi upon t. So I have said write 2 pi upon t whole square is equal to gm upon r cubed. So this is 4 pi square upon t square is equal to gm upon r cube. If I invert this, suppose I can write t square upon 4 pi will be equal to this r cube upon gm. So I can write t square is equal to 4 pi square upon gm into r cube. Now you can see this entire thing is constant. Actually this can be the formula for the time period, but this entire thing is constant. So I can say t square varies as r cube, that's it. So that's the Kepler's law. It says square of the time period is directly proportional to cube of the orbital radius of the satellite. Now you can use this ratio method. You can say t square upon r cube must be constant. So I can have a formula t1 square upon r1 cube is equal to t2 square upon r2 cube. This formula is very much useful when it comes for the bodies, for the satellite of same bodies. Suppose if this is here m and other body of mass, suppose m2 is here, this of m1 is another satellite, and even in the same orbit, or it cannot be the same orbit, suppose in another orbit, it's m2 or its mass is m2 or even m, then you can use this formula for the same satellite. This is valid for suppose for the Sun, Neptune, Mars, because these satellites are of the satellites of the Sun, Neptune, Mars, Earth, Saturn, so many these satellites. So you can use this for the Earth and this ratio, and also you can use for the Moon and the artificial satellite, because the Moon is the satellite of the Earth and also the artificial satellites of the Earth. So we can use this one. Please keep in mind this formula can be used if this 4 pi square upon g m is constant. This m is constant if the satellites are revolving around the same body. So this formula is a ratio method, but it's valid when there are the satellites of the same body. Now suppose I have to find the potential energies and kinetic energy of satellites. Suppose if I have to find the potential energy, kinetic potential energy of satellite is equal to m phi. So potential energy of satellite is m into phi is minus gm upon r. So potential energy of the satellite becomes minus gmm upon r. Potential energy as usual is negative. Similarly, I can find this is the formula for potential energy of the satellite, and potential energy of the satellite is given by EP is equal to minus gmm upon r. Similarly, I can find the kinetic energy of the satellite. Kinetic energy of the satellite is given by just using mv square upon r is equal to gmm upon r square. Do not cancel mv square r. This is mv square will be equal to, I can write gm upon r. If I put here 1 upon 2 mv square, it becomes gmm upon 2r. So this is nothing but the kinetic energy. So kinetic energy is gmm upon 2r. You can see kinetic energy is positive, potential is negative, and actually kinetic energy, I can write kinetic energy as half of what? Potential energy. If you multiply by half, this becomes just the kinetic energy. So kinetic energy is half of the potential energy, but keep in mind, kinetic energy is positive and potential energy is negative. I can find the total energy formula. What the total energy is? The total energy, I can find total energy is E is equal to EP plus EK, and if I add these both, minus gmm upon r plus it is gmm upon 2r. I can find the LCM is 2r. So if you simplify, this becomes minus Gmm upon 2r. So this in magnitude is same. Now see, there are three formulas. For potential energy, the formula is minus Gmm upon r. For kinetic energy, the formula is Gmm upon 2r. And for total energy, the formula is minus Gmm upon 2r. Now total energy must be negative. Why is total energy negative? It indicates that actually you have to do some work to dislodge the satellite from its orbit. That's why it's negative. Another useful formula is we can have a relationship between the energies. And the energies always first you should keep in mind that EP and E means potential energy and total energy are negative quantities. First. Second one, EK is always positive. Now examiners usually give one type of the energy and this asks to find another type of energy by using, suppose they give E as this one and you have to find EP and EK by using these concepts. EP and E are all negative and EK is positive. Kinetic energy is always positive. Potentially and total energy are negative. But in magnitude, total energy and kinetic energy are always same. And total energy and kinetic energy are always same in magnitude and they are always half of what potential energy magnitude. So this is the relationship between these two. I can find the graph between these two. Suppose now I have to find that is a total energy. This is the orbital radius. And suppose this is the radius of the planet or something and this is the total energy E. Now clearly within the surface of the planet there cannot be the satellite, so the total suppose kinetic energy is always positive. Suppose I am taking this as the kinetic energy, so this goes like this one, this is the kinetic energy. So clearly kinetic energy, when orbital radius increases, the kinetic energy also decreases. That's why the speed of satellite is decreasing. That's why if the satellite goes away from the Earth, its speed must be slower, linear speed, because kinetic energy decreases. Similarly, the total energy must be same in magnitude as that of kinetic energy. So if this is, suppose this is 4 centimeter, this must be 4 centimeter, this is minus E. Now what about the potential energy? Now potential energy is double. Actually potential is double than the kinetic energy. So this must be potential energy double. So you can have from this thing. At any point, suppose if I say this is suppose 2, this is suppose minus 2, this must be then minus 4. So potential energy must be minus 4 then. So clearly if this is 2 centimeters, this will be 2 centimeter, but this will be 4 centimeter. This is for total energy and this is for potential energy at any point. Now see, sometimes examiners say what happens if the orbital radius increases to the kinetic energy, kinetic energy decreases. What happens to the total energy? Although total energy magnitude is decreasing, but actually it increases because total energy is negative. Similar is the case with the potential energy. But in all cases, at all time, sum of potential energy and kinetic energy must be equal to total energy. Now there is only one thing, how to find the work done. What is the work done while lifting the satellite from when you are lifting it from, suppose, surface of Earth. Suppose if this is the surface of Earth, the mass of the Earth is m, its radius is re. You want to lift it and its orbital radius is r and you put the satellite over m. What should be the work done? I can have the work done from the formula of work done. I can use this one from the surface of the Earth. I can say EP at surface of the Earth, EP at surface of Earth plus EK at surface of Earth plus work done must be equal to here EP plus EK. So this is EP at orbit, EP at B, and EK at B. This must be the total energy. So EP at surface of Earth is, EK of surface of Earth is 0. So I can say work done by lifting the satellite is always equal to total energy minus EP at surface of Earth. By this, we can always calculate the work done by lifting the satellite up. It's very simple. EP at the surface of Earth plus EK at the surface of Earth plus work done must be EP at B plus EK at B. This is the B point, suppose, and you know EK at the surface of Earth must be 0. It's always a test. There must be some EP, and work done we have to calculate. This becomes the total energy. So total energy minus EP at surface of Earth. I can also write work done. Total energy is minus GMM upon 2R minus EP at the surface of Earth is minus GMM upon RE. I can simplify these formulas also and can find the work done.